Welcome everyone, thanks for coming. This is awesome. We have actually more people than last year to come to the Vision BOF. You know, Vision is not necessarily central to SIGGRAPH, but it's becoming more so, so we're glad to see you here. And we're going to be talking about vision processing in general, what are the kind of the libraries and APIs that are out there. And in particular, we'll do a bit more of a deep dive into the vision API that Khronos is developing, called OpenVX. I'm Neil Trevett. I work for NVIDIA and I'm president of the Khronos group. And for those of you who haven't met the Khronos group before, we're an open consortium. Any company can join. We do low-level APIs for graphics, compute, parallel computation, vision processing, and we love people to come in, join, help us make the APIs that the industry needs. We have everyone from Google and Apple all the way down to small companies helping us put these APIs together. And vision processing is becoming more important for SIGGRAPH because it's a part of the visual computing loop. You know, in SIGGRAPH we're focusing mainly on the graphics process, which is taking data and turning it into pixels. But vision processing is the opposite. It's taking pixels from a sensor, a camera sensor, and turning it into understanding and data that the application can use. And as we move forward into advanced augmented reality type applications, that glass, for example, is not there. That's a virtual glass, but it's interacting in very sophisticated ways with its environment. That's possible because of high performance vision processing. And vision acceleration and vision processing is enabling waves of new types of applications and use cases. We've had computational photography and computational videography for a while, but now it's becoming much more common to see cameras being used as input devices, gesture processing, body tracking. There have been quite a few BOFs and sessions around I've seen on using cameras to reconstruct 3D models. And again, kind of the holy grail of vision processing in some ways is to look forward to seamless integration of reality and augmentations in applications like augmented reality. So, getting to your acceleration cores for vision processing is obviously a vital part of developing any vision app. And there are quite a few vision libraries out there. Probably now the best two known are Opencv, which has been around for many years, an open source project, and up and coming is OpenVX from Khronos. But there are general compute APIs out there too, and it's a question we often get asked, which is why we've done this little introduction. Should I use a library or should I use a general purpose parallel computation framework? And again, the framework that Khronos is developing is called OpenCL. So I'm going to start and spend just a few minutes kind of comparing and contrasting what does OpenCL give you, what does OpenVX and OpenCV give you, so hopefully it'll be useful if you're trying to make your own decision on what to use. So starting with OpenCL, it's a general purpose computation framework. It's designed so you can interrogate and find out all of the compute resources in your system. It can be CPUs, GPUs, but also DSPs, FPGAs, and even hardware blocks. And then you can write kernels in a kernel language, which is primarily C, soon to be C++, and then you have the APIs that let you compile those kernels and distribute them onto any of the available processors and gather back the result. Now, of course, you can do anything you want in such a general framework, and you can certainly do vision processing. And it's actually interesting to note that for many applications, like autonomous driving, driver assistance, in the automotive industry, a lot of the vision processing is actually transitioning from classic vision processing pipelines to neural net and deep learning based systems. And a parallel computation framework like OpenCL is ideal for accelerating neural net type functionality. To compare that to OpenCV, OpenCV was originally initiated by Intel many years ago. It's now an extensive open source library. There are thousands of functions. You can do pretty much anything you can imagine in OpenCV. It's put out there in a free use BSD license. It's optimized in C++. So I would say that the main focus on Opencv is exploration and prototyping, and you can run Opencv pretty well anywhere. That focus on the past hasn't been so much on figuring out how to accelerate it, but that's becoming more and more important to the Opencv community. And they're using OpenCL, so it's actually quite interesting to see Opencv and OpenCL begin to work together. So Opencv 3.0, which is the latest version, has a thing they call the transparent API. So if an OpenCL implementation OpenCL runtime is available on your system, the Opencv stack will take advantage of OpenCL and begin to accelerate the available primitives that are coded in the OpenCL framework. And we actually had a very good conversation. We have a good, Khronos is very supportive of Opencv. It's complementary to OpenVX, and we try to have a good open dialogue. The convener for Opencv is the chair of OpenVX, so the communities are very close. And we kind of get to, well, how is OpenCL, how is this acceleration thing actually working out in practice? And the straightforward state-of-the-art is on desktop machines, PCs, and Linux. The OpenCL layer is pretty robust, and you can get pretty reliable Opencv acceleration. We're not quite there on mobile yet. There are lots of OpenCL drivers on mobile devices, and if you're interested in that, this OpenCL BOF is next, and we'll have a lot more detail. But performance portability is not quite so easy on mobile. Mobile devices have slightly different characteristics. The caching doesn't work out quite so portably. But we're working on it, so we're hoping over the next couple of years that even on mobile, OpenCL and Opencv will be a good pair. But the thing that's really driven OpenVX is the realization that OpenCL is great, but you have to kind of power up your CPU complex and perhaps a GPU complex. That's kind of the things that OpenCL are built to do. But we have use cases like the augmented reality glasses that we're all dreaming of in the future. That's going to need to be on all day, constantly scanning the environment with a thermal limit much lower than your phone. And that's a very hard thing to do. In fact, that's not actually really possible yet. So the challenge is to deliver vision acceleration at the next step down in terms of power, and much more power efficient. So how can we do that? Well, dedicated hardware is definitely going to be part of that solution. CPUs are great in general purpose, but for vision and parallel compute, GPUs are more power efficient, and dedicated hardware, if well designed, can be yet more power efficient still. So we need to have some vision frameworks that are targeted for portability and extending that portability reach into low power dedicated hardware for vision acceleration. And that was the original inspiration for OpenVX. So OpenVX is a Khronos standard, so it's royalty free, it's available to anyone to use. It's targeted at mobile, real-time, low-power applications, this gap we have in the ecosystem. But it's portable across any system that you would want to run it on. You can tap into ISPs, image signal processors, dedicated hardware, DSPs, DSP arrays, GPUs, multi-core CPUs, anything that you have available in your system. And the interesting thing about OpenVX is that once you set up the processing graph, which we'll get to in a second, you don't need a particularly high-performance CPU. You don't need to have multi-core CPUs, second battery. The graph maintenance can be a very low-power operation. And I mentioned the OpenVX graph. The graph concept is really the key to power efficiency in OpenVX. Opencv, in its standard state, is a memory-to-memory model. So if you have a vision operation like a filter or some kind of detector, Opencv, in default, you would read the whole image, you would do the function processing, and then you would write the result back, and then the next function would read the image again. constant round tripping to memory, particularly on a mobile device, is very, very bad. Very, very bad. You don't want to do that because you don't have the bandwidth to start with, and that's the most power-hungry thing you can do, is be reading and writing at high bandwidth with adequate memory. So OpenVX has a concept of a graph which is expressed up front before anything starts to execute. And the fact that the implementer is given the graph topology, it gives the opportunity to the implementer to optimize how that graph is going to execute in practice. So it depends on your implementation. You might want to coalesce some nodes together. If you're running on a GPU type device, a common technique is to slice the image into tiles and send tile-sized chunks that will fit into cache, so from input of the graph to output of the graph. So you avoid all of the memory round tripping. So OpenVX and OpenCV are quite complementary. Comparing and contrasting, OpenCV is an open source. OpenVX is an API that's tightly defined with conformance tests. OpenVX doesn't have the breadth of functionality of OpenCV. We're much more focused on the typical mobile applications. But OpenVX is extensible, so if you find some functions are missing, you can add them, and people will be adding functions to the core specification over time. People using OpenCV would typically take the source code and port it onto their system. OpenVX is intended to be implemented by the silicon vendor and offered to the developer as a kind of built-in library. And they both have their strengths and weaknesses, but OpenVX for low power deployment. Now we're actually finding that OpenCL now is being used to accelerate OpenVX. You don't have to use OpenCL, but it's certainly one option that implementers have. If you are running OpenVX over a GPU with an OpenCL framework, then it can be a good way to get acceleration. So what we're finding is that people are using OpenCL in some cases to code their nodes or their primitives and providing the full range of OpenVX primitives to their developers. And then the developers don't have to go down to the OpenCL level. They can stay at the higher level of abstraction, which is the OpenVX graph. And it's much simpler to work with OpenVX, plug pre-installed nodes together in your graph topology than it is to have to worry about low-level OpenCL programming. So OpenCL and OpenVX are also complementary. General purposes and low-level OpenCL versus the high-level graph-based topology of OpenVX. You could not run OpenCL on a very low-power core without IEEE floating point, but OpenVX lets you run on any range of hardware, including a very low-power hardware-based system. So in terms of the overall status, before I hand over, we launched the 1.0 OpenVX spec in October 2014, so OpenVX is still quite young. It's less than a year old, so it's quite good to see momentum already building. We did a maintenance update to the spec in June. There's an open source sample implementation that you can download and try. We have a full conformance test suite, an adopters program. The first conformant implementations are beginning to flow through that program. You can see it's kind of a who's who of the vision industry, helping us build and promote OpenVX. So that's it for me, and we'll have time for questions at the end of the session. We have a number of speakers here. Andrew Garrard from Samsung is going to be speaking about a related initiative at Khronos, a data format specification, and then Radha from AMD is going to be deep diving into the technicalities of OpenVX. So let me hand over to Andrew. Thanks.
Where we were supposed to come in, but okay. Excuse me, however, while I get into presenting. Neil, do you know how to drive your laptop into presenting?
No, you don't.
Because speaker notes now. really drive computers around it. Yes, hello. Okay. Oh, I know what you've done. Sorry. This looks much better when you're in the split screen mode. Excuse me for my high sun. Right, pretend you didn't see that. I will be. We're well-oiled machines. Yeah, could you please drag that window onto this? That's really much quicker than you press it in your plan. Anybody see a mouse pointer? Thank you, technology and everything. Neil, I seem to be in your presentation, not mine. With mine, you've integrated. Ah, that's my thing. Sorry, the problem with running over from SIGGRAPH is that it's hard to tell where we are. Can I have some way of changing the slides? That thing where it's stuck in things it's presenting. It's probably going to be this thing. Find this nomination. Right, you see if you can fix that.
I've never managed to get speaking to work ever.
Is there a software engineer in here? I think it thinks it's doing, yes, he's presenting you. and I think it thinks it's still presenting. Microsoft. Don't worry. Okay, sorry. Right, good news. This is a short talk, and I apologize to Radha for all of his time I've just taken. Hello everyone. Hello everyone. You awake? Yeah. So this is a talk about communication, and this is about the latest Khronos specification, which I would love to say is terribly exciting because I wrote it, but actually it's extremely dull. It's a really simple thing. So the good news is that some of you can go to sleep. Except if you're writing a program that works with pixels or with textures, and that's stored in memory, and you need to do anything with that that other people might understand. And if you have more than one type of that kind of thing, or if you're dealing with hardware or anything like that, in which case 2 minutes of your time, please. So formats. We know what texture formats are. You've got some bits that correspond to pixels or textures or something like that. And we want to describe what they mean. And a lot of APIs actually don't care what they mean. In something like OpenGL, it doesn't really care what the RGB channels are for. They're just called RGB. That doesn't necessarily mean red, green, and blue. But maybe you presumably do care. So when you say, I work with RGB, what do you mean? Well, what RGB? Maybe you meant obviously 32-bit, because that's the obvious thing to work with. Or maybe you meant obviously 16 bits, or a different 16 bits. And maybe that order was the obvious one for you, and that's what you decided to use, but different APIs have different ideas of which order is obvious. And you're doing this for a little bit, and then it doesn't really seem to work. So you find yourself trying to work around different implementations for a while, and then that happens. Then you decide that you've actually worked out which pixels are which, and it doesn't quite look right. So you pick the standard colors to see what happens, and then you find out which bit is in the right channel, but you don't know what the channels mean. So if you've got the obvious colors, that's fine. But then maybe you've got the range slightly wrong, so everything looks a bit dim. Or maybe you've got the gamma wrong, so everything looks a lot dim. Then maybe you've got things like sRGB to worry about, or you're outputting to a TV. And then there are lots of TV standards, because of course there are. So you have to deal with all of those, and then you make a guess at what thing might seem obvious. It looks all right to you, and then one of your colleagues is trying to standardize it, and then that happens. And then you decide, oh, it'd be a good idea to support YUV, and then you realize there's more than one YUV as well. In fact, there are a lot of YUVs, and then you try to use compressed formats as well, and then you try to use input from a camera, which turns out to be in a weird Bayer pattern, and there's a load of metadata, and it all gets quite complicated. And then you have a really intelligent application that you worked everything out for, and you have a really intelligent API that you're trying to connect to display all of this correctly, and then you plug in a stupid library in the middle that can't work out all of this, and all the metadata goes missing, and that's annoying. And so around this time you realise that all of this is quite complicated, nobody does this quite right, and you end up doing that kind of thing. So nothing does this right pretty much, because everything concentrates on just what you need for the problem space that you're working with. GL knows what RGB is, GL understands RGB, GL doesn't need to know about all of this other stuff. For example, VX knows about some YUV formats, but doesn't necessarily know about camera formats at the moment, that kind of thing. And then at some point you need to expand whatever API you're working with or libraries you're working with to handle other things. And everybody thinks it's really simple, so everybody rolls their own. And then you try and make them talk to each other, and you find out what happens when everybody rolls their own because they're all different. And then you think that you had this little API that you wrote that wasn't doing very much, and then suddenly you find out that everything is interconnected. So, why am I standing here? There's a data format specification. It's just been released. This is the first big thing we've stood up and said about it. So we've said OpenVX isn't new, that's nothing. We're talking 2 weeks for data format spec. It is an extremely dull thing. It's the thing that everybody thinks they can roll their own for. Please don't. It's descriptive, so that rather than having a big enumerative list of what all your textures, what all your formats are, you can actually write general purpose code that can handle anything, including the wacky format that your manager is going to come and ask you to support next. It's extensible, so you can put in proprietary extra information. Standard hardware vendors can put in extra stuff. It's versioned, so when we made a mess of it, we can update it. It's flexible, it supports every format I can possibly think of, and I can think of some really wacky formats. It's not big, it's only a few pages. You can go and read it on the toilet. If you print it on soft paper, you can dual purpose that. There are no conformance tests for this. This is just a thing that's Khronos is donating to the industry because we've been bitten and we'd like you not to suffer the way that we have. It's not tied to any specific Khronos spec. It's covered under the EGL group's auspices, but it doesn't rely on EGL. You don't have to care about Khronos to use this thing. And you can feel really superior because the press release went out a couple of weeks ago and absolutely nobody in the press knew what to make of it because they're not software engineers. So, this was my fault for using practical effects to SIGGRAPH, of course. But to avoid suffering in the same way that I've suffered with this kind of thing, please take a look at the data format spec so you don't have the kind of problems that I've been having, and I can never do this ever again. Thank you very much.
It's worth it. So, whilst Ron is plugging in, does it have any questions for Andrew?
So what does it mean? So the idea is that, so if you've met something like the 4cc formats list, where there's a list of ways that say this is, if you've got RGB in memory, then we have one format as a way of saying things are, we've encoded red in the first 8 bits and green in the next 8 bits and blue in the next 8 bits. And then there may be a series of other enumerations that handle other different things. That has one list that's not canonical and doesn't describe a load of useful stuff that you might want to know when you're trying to understand your data, and doesn't understand a load of compressed formats and that kind of thing. GL has an internal list of what its formats might be. OpenVX has an internal format list as well. So I'm expecting every API to continue doing their own thing as much as they need to, but the idea of this specification is it's just a standard memory block that lets you describe what you meant when you described a particular format, and then you can use that for documentation, and you can use that for passing it between APIs, so that everybody understands each other, and we'll get along.
Hi, my name is Radha Giduthuri. I work for. How about now? Can you hear? Okay. My name is Radha Giduthuri. I work for AMD, and I'm also a member of OpenVX working group at Khronos. So in this presentation, I'll brief you over OpenVX API with some examples to get you a sense of how the API looks. Right? So let's get started. OpenVX 1.0 specifies a framework and core set of vision functions that can significantly accelerate by can be accelerated by diverse hardware, ranging from completely programmable processors to a dedicated hardware pipeline that Neil was mentioning about, GPUs, DSPs, a wide range of platforms in that. And it is intended to be used either directly by a computer vision application or as an acceleration layer to be used by some higher level vision frameworks such as OpenVX that you mentioned, or a lot of other frameworks that will come forward, and also be useful by some third-party vision engines or any platform-specific APIs underneath. When we were coming up with this spec, we had two main goals in our mind. And like any other OpenVX, any other Khronos API, we wanted to come up with a standard framework that can be used on a wide range of platforms, and also define an API in such a way that vendors have opportunity to accelerate to minimize the runtime overhead underneath that. So let's get some more details here. In terms of the functionality, it starts with supporting the basic data types that are very essential to computer vision. Now it all starts with images. They are all opaque objects, so they can be easily mapped to various kinds of hardware. We have to support not only CPUs as well as go to GPUs and fixed function hardware, so you may not be able to access these pointers directly from a host without having any particular API in the framework. And in terms of the functionality, there are OpenVX 1.0 mandates most commonly used functions for computer vision. Here are a few of them that are listed here. In terms of the computer vision processing, for the image processing, there are basic pixel-wise pixel addition, subtraction, multiplication, and logical operations. And there are various kinds of image formats that are supported here, going from RGB, YUV into some just plain or 8-bit, 16-bit images that may not have any color correlation with them. And you may be able to convert the bit depth, being able to convert the color from RGB to Luma or YUV. And you'll be able to apply some filters, 2D filters and convolutions, such as Gaussian filter. You can apply box filter, morphological operations. You could resize images from different sizes. You could also apply some affine transforms, either affine transforms or perspective transforms, kind of going from one type of image to another type of image. And two data structures that stand out in OpenVX that are one are pyramids, and another one is integral image. Pyramids are extensively used in computer vision algorithms. It's pretty much think about an image got scaled down successively going down. So to improve the performance, perform operations at a low resolution and then successively go up scaling the operations in that. Another one is integral image, which gets used in object detection kind of algorithms. To mention a few other operations here, there are feature extractions such as Harris and fast detectors, and there's optical flow. Now, in terms of overall function, what Khronos defines is a basic framework and a basic framework that developers can use to create and manage graphs and also be able to execute graphs. And we kind of come up with 41 functional primitives that are widely accepted by the industry, at least the Khronos members here. And then once now the vendors are free to extend this functionality to add their own functionality. Once all the functions gets accepted by the industry, it will go back to the Khronos and we'll try to add more and more functions into the spec. Just to get started, I want to start with a simple example so I can illustrate some of the terminology here. So here is an example where an image is coming from a camera, RGB image, and then we're going to detect some features such as some kind of corners, and then blend it, overlay it onto the image, and display it in the output. So here you can kind of see there are an RGB is the image is represented using a VX image object, which is kind of an RGB image. And then at the bottom you see there's a VX array, which is a key points where you have an array of XY coordinates which kind of indicate what are the special points in the image that are of interest here. And then you see the rectangular blocks here, which are called as OpenVX nodes, which are nothing but an instances of a particular functionality, which is an abstract node, which is an abstract function. The one to notice is at the bottom there's something called Khronos, which basically takes a Luma image, which is a grayscale image, and then identifies the corner points in there, and then gives it an output to the array image. So overall, the points to note here is there is a node which is an abstract functional block, instances of an abstract function, and there is VX image and VX array, which are kind of type of data objects in OpenVX, and all these things is wrapped under an OpenVX graph that can be scheduled in any hardware domain. OpenVX objects are both strongly typed at compile time for safety critical applications, and also are strongly typed at runtime for dynamic application. You can take an OpenVX object and then downcast it to VX reference, and that reference will retain what type of object it is, whether it's an image or an array or pyramid, depending on whatever that is. So for dynamic applications, all these objects are very opaque, and the strong types are very essential. If you can try to compare this with OpenCL, kind of a model where you have a memory object as a general object, which can be used as an array or as an image. There is not much information given about the object to the framework, so the framework doesn't have much knowledge about how this object is being used. The fact that OpenVX defines various kinds of objects, now the framework knows about it, and implementation can take advantage of that knowledge to further optimize, because it knows the usage patterns, what the data represents, things like that. And at a high level, from the framework perspective, there is a context very similar to OpenCL, if you are familiar with, which basically is, encompasses of all the objects that reside under. And there are other objects like VX kernel, which basically is an abstract function. Example is Harris function that you've seen in the previous example. You could have color convert functions. All the functions are kind of abstract, can be represented as a VX kernel. And we went over the graph and node. Let's keep the parameter for now. So I just prepared this slide just to give you an idea about how various objects look here in the OpenVX. One is an image. There are various data types that OpenVX supports, ranging from a single planar image of 8-bit or 16-bit or 32-bit to a multiplanar images such as IOIUV or NV12. And also it supports interleaved formats such as RGB. And you can kind of consider a pyramid as a multi-planar image, but pyramid has a particular semantic built into it, which basically says that each successive image, each successive plane represents a same image at a reduced resolution, which is scaled down using certain kind of smoothing filter underneath. Besides pyramid, there is an array, which is a chunk of memory which has a certain capacity. You can, at the end of a writer, a function that writes into an array basically can continuously add the elements to it. At the end, it basically tells you, at the end of writing, it tells you how many elements are in the array. Now, input to the array can pretty much read only up to that, and the capacity pretty much limits the how much memory you can write into that. OpenVX 1.0 specifies certain data types that can be used as an array element. One is a key point, which basically pretty much specifies XY coordinates, followed by some kind of string and other metadata associated with it. And there are other items such as rectangle. If somebody writes a kernel that identifies, for example, faces, and you want to, given an image, you want to give a list of faces, so it kind of can be represented as rectangular boxes in there. And somebody can extend OpenVX to with their own data structure that I kind of mentioned that as a user-defined structure here. What other classes are there? There is a scalar, which is kind of a very a primitive data type, such as integer scalar. Sometimes a lot of these functions take configuration parameters, such as some kind of a threshold or a strength thresholds that can be represented using a scalar. VX is a very interesting data type, which basically it contains a list of temporarily delayed objects, which can be implemented using a recycle, kind of a ring buffer in a kind of that goes in a round robin fashion. So at any given instance of time, imagine a kernel has access to an object at t0, t-1, t-2, kind of going forward up to whatever the delay that you need to support. And when you try to process next one, you can kind of increment the, you can add a delay into that, so that way all the buffers will get shuffled around. Now then the kernel function will have access to all the set of functions with the same index going from 0 to whatever count that is available in there. Where does this get used? You can think of it in kind of optical flow, where you're kind of looking at the image at the current time frame and the image in the previous time, so that it can look at the delta from previous to current. You can also look at it as a pyramids, for example. You want to look at a pyramid at the current time 0 and also time t-1. So what it buys you is, once you compute a pyramid, you can put it in this delay element, so that way it kind of goes back and forth. You don't recompute the same object multiple times. Here is another depiction of the OpenVX framework. You can kind of see all the objects stay within the context. There's one object that I introduced here, which is called a virtual data object. A virtual data object pretty much stays inside a graph, which is kind of for mentioning that this is an object that is temporary, which won't be accessed by the end user. So what you're telling the framework is saying, this object is not used by the user. You can allocate it wherever you want, and since it is not getting accessed by the user, the underlying framework can fuse some functions, even get rid of this memory altogether. So it kind of gives a flexibility for all the vendors to be able to optimize more. And there are some extensions in terms of that can be provided by a third party building more kernels, kind of loadable kernels that can be done here. This has a lot of data here, a lot of points here, but I think one point that I want to mention here is the graphs have certain rules to follow. One of them is you cannot have cycles inside a graph. That means the rules that Khronos OpenVX spec provides here is there can only be one writer for a data object, and the data can only be read after it has been written. I think I'll have more details of this covered in some of the examples that are going to come forward. Now let's look at the graph lifecycle. You create a graph, and before you execute, you have to do something called, you have to verify a graph. Now verifying a graph just means that you're asking the framework to say, I've constructed the whole graph, make sure there's nothing wrong with it in terms of all the consistency checks are made, all the data types that are given are supported by the underneath frameworks. And if there's any optimization that needs to do, now the underlying implementation can mark those optimizations and give it to the runtime when it tries to execute. Now for execution, there are two kinds of modes it supports. One is a synchronous mode, where you just say VX process graph. As soon as the function returns, you know that all the outputs are available. And the other mode is asynchronous mode, where you simply issue a kind of a submit, a VX schedule graph, where you're simply telling the graph saying start executing, and then the function returns immediately to the host code. And now when you want, so that the host code can continue processing something else, and when it wants to wait for the results, it can call simply wait for the graph. Now the thing here is, once you verify, you can keep running the same graph again and again. The only time that you need to re-verify the graph is sometimes if you all of a sudden, let's say you give another, you change the camera, or your image resolution changed all of a sudden. Now you want to kind of ask the framework to verify it again, because a lot of the assumptions that were made are not applicable anymore. It is a simple example that I took straight from the spec. In this example, you can see the input is a UI/VY image, which is a YUV image in a 422 kind of decimation, and the output is basically gives you the edge magnitude. It basically runs a Sobel gradient, and then followed by looks at the magnitude, saying how strong the magnitude is. It also gives you a phase in there, and you can see the intermediate results here are virtual graphs, and it initially takes a UI and extracts the luma out of it, and then performs the smoothing followed by gradients, and then on the gradients it calculates the magnitude and phase, which is magnitude is basically a square root of x gradient and y gradient. And in this particular example, you can see it starts by creating a context, and at the last line, if you notice, there's a release context. Now you can think of this as the life cycle of the context. Once you say release, all the memory allocated under this context will all be released, so you don't need to keep track of every object in there. If all you want to do is just create once and then destroy it at the end. Right? And in this example, you can also see that the images that are created here are UI/VY, which is the input, and the 16